Hey Ainsley, it's Christian. So I've got a bad cold. So sorry it took me so long to do this. But here is kind of what this page is talking about. The first thing they start talking about is spring potential energy. So if you've ever taken a rubber band and you've stretched it and then let go of it, but you're still holding on to the other side, you know that a spring or anything that kind of acts like a spring, like a rubber band or a bungee cord, it has energy because it hurts when it comes back and hits you. So if you ever had anybody shoot a rubber band at you or anything like that, that's essentially a spring. So springs have potential energy, and we use what we call Hooke's law in order to help us figure out how much energy it has. And we know, if you remember from springs, the force of a spring is equal to the spring constant, and that's that K value that tells you how strong the spring is, times how far you stretch it. And because work is equal to force times distance, what we can do is we can say that's kx times x, which would be kx squared. But for some reason, there's this half thing in there, and that's because when you stretch a spring, you essentially have a force that's increasing in proportion with the stretch. So when I stretch the spring, as I pull it, then it makes this triangle. And the area underneath the triangle of force versus position is your work. And that's also the potential energy. So whenever you stretch anything like a spring, it takes work to do that. Notice that this spring constant is really small. So this might be like a slinky. And I'm going to go through, and the first thing I'm going to do is I'm going to show you a force plot. So if I take this little guy here and I want to pull on this spring, I can plot the force versus how far I stretch it. And you'll see that it can have positive force if I stretch it, and you'll see I get positive potential energy. And then if I compress it, when I compress it, I also have more force, but notice that that force is negative. But even though the force is negative, you'll see the potential energy here is still positive. And that's because we said that the work or the potential energy of the spring is 1/2 kx squared. So even if your x is negative, like it is here, because we square it, you get a positive amount of energy. So that's kind of the nice part. We don't get negative energy with a spring like we do if we have gravity. And remember, we got negative energy when we made the top of the hill 0 and the bottom of the hill negative. So we had like negative 100, I think, on one of those. So that's what it looks like. If I go to an energy plot, you'll notice that no matter which way I go, whether I stretch the spring or I compress the spring, that energy is always going to be positive, and it follows a curve. Because remember, our equation is 1/2 kx squared, and that is a parabola, which shows you that x squared nature. For a bar graph, we can just see how that potential energy goes up, just like we did earlier. And so as I move this back and forth, you'll see that. The best thing to do here is to look at the, if I change the spring constant, what's going to happen to the energy. So notice that when I do this, it finds the area under the curve, and that's that blue part, and that's the amount of energy it has. Same thing on this side. My question is, if I increase the spring constant, and let's say I make it 200, that means the spring is thicker, it's harder to stretch and harder to compress. And if you watch the graph up top, you'll notice that this graph, as I do this, gets steeper. And so now when I move it, I have to do more work to stretch it, but when I let go, it should come back to the middle. And then if I do this, same thing. And so you'll see how that kind of works. If I really make this big, I'm going to get a lot of energy compared to what I did before. So hopefully that helps a little bit with kind of how spring energy works. The last part here is the conservation of energy. So in this example, you've got a toy car, and they push the toy car back, and then they let go of it. And when they let go of it, the car goes up this hill, and then it stops up at the top. And it's because the work done by the spring gives it kinetic energy. So here we're going to have spring potential energy. So I'm going to put PES for spring potential energy. And then that gets converted into kinetic energy. So it has all kinetic energy here. And then as it goes up this hill at the top, when it gets done and its velocity is equal to 0, now it's all potential energy due to gravity. But right here in the middle, I'm going to have part of that energy is going to be potential energy due to gravity, and part of it's going to be kinetic energy. But no matter where I am along this path, as long as there's no friction, I'm going to have the same amount of energy. So let's say that this energy was 100 joules. That's converted to 100 joules of kinetic. And then halfway up, it might be 50 potential and 50 kinetic. And then at the top of the hill with no speed, it's 100. And it's 100 joules no matter where I am, because I always add all the different things if there's more than one together. Notice that if it goes along this alternate path, that it's going to have potential energy here, it's going to have kinetic, but then it gets more kinetic as it goes down. And then when it comes back up, here, the energy is just going to be 100 joules again of kinetic, and then it's going to come back down and then come back up, 100 joules of kinetic here, and then 0 kinetic and all potential energy here. So this path doesn't really matter if I'm going from here to here. I'm still going to have 100 joules here and still 100 here. If you include work, that means that you're just either adding work in or you have work coming out of your system. So you'll see that. They've got NC here, and that's non-conservative work. So non-conservative work is work that you lose. So for example, let's say that I've got a person, and that person is pushing a box against the floor. And let's say that when they do this, they end up with 100 joules of work. When they let go of it, it has, so this would be work in is 100 joules. It's moving at its fastest speed here. So this is V max. And so it's going to have 100 joules of kinetic energy. And then as it slows down until it gets over here where it has 0 joules of kinetic energy, we know that in the middle it's going to have 50 joules of kinetic energy, but it's lost 50 joules of energy due to non-conservative forces like friction. And that friction then makes heat. So you can lose energy due to heat. You can also use it due to sound. So if you think about if you push a box across the floor, it slows down and stops, and a majority of that is released as sound, that extra energy. It's converted from kinetic energy into sound. And sometimes you even get light. So there are some processes, like if you compress air, it'll actually then heat up really hot, and you'll see kind of a flash of light. So the sample that they have here is how you can lose energy from friction. So it says, how far will the player slide on the ground in the following situation? So they've got the mass of the person is 65, the velocity is 6, and we know that our final velocity here is equal to 0. The force of friction on this person is 450 newtons. So what we can do is we can say, well, that's the only force, and it's going to slow the person down. If that's the force, and we know the mass of the person is 65, we can find the acceleration of the person. So the force net on this person is equal to the person's mass times their acceleration. And if I did a free body diagram for this person, I would see that I have straight down is mg, straight up is the normal force, and then to the, let's see, friction is going to be to the right. Sorry about that. And so what I can do is I'm going to get rid of that arrow to the left, and then this is the force of friction. So our net force is equal to this, and the only force I have acting on the person is the force of friction. And that is equal to the mass of the person times their acceleration. So if the force is just friction and it's 450, and we know the mass is 65, then we can easily find the acceleration. So if I do 450 divided by 65, I get an acceleration of 6.92 meters per second squared. Now, because they're slowing down and our direction of motion is to the left, this acceleration has to be negative. Since they're moving left and the friction is to the right, in order to slow down, I have to have a positive velocity, therefore a negative acceleration. So now I know what the acceleration is. I can very easily find how far the player will slide by just using Vf squared is equal to Vo squared plus 2 times my acceleration times the change of position. So this is 0 is equal to 36 minus 2 times 6.92 times delta x. And so 36 divided by 2 times 6.92 is going to be equal to a change in position of approximately 2.6 meters. So, you know, of course, there's more to this. I think one place that you can go that will give you a lot more information that will actually kind of teach you some things is if you go to Flipping Physics, and then if you go to, and I know this is AP Physics 1, but it's okay because he'll put it in a really easy way for you to understand. But if you go to AP Physics 1 for teachers, you can go down and you'll see here's work, energy, and power. And you'll notice that here's conservation of energy. And what I would do is just open this up and take a look at it. But you can also learn about work, look at an introductory work problem, look at kinetic, gravitational, and elastic energy. Those are the three that we've been dealing with. And then look at conservation of energy. Here's another one, the conservation of energy. Here's one with friction on an incline. So all of these would be really, really good, I think, to kind of help you understand what's going on with those. So if you look at some of those, of course, you don't have to watch the whole thing. Definitely don't have to do the Ed puzzles. And you can watch them at a really quick pace. You can always speed them up on YouTube. But if you just open that one up and then actually play it in YouTube, you can actually then just go over and you can change the settings and make that playback speed so it's super fast. And then you can just read what's going on. And so, you know, they're entertaining to a certain point, but this will really kind of show you some things that I think I can't show you unless you and I meet. So hopefully that's helpful. And I will be quiet now because I've gone on for too long. So have a great night. I will talk to you later. See ya.